All right. Thanks for joining this session. On behalf of my co-authors, I'm happy to present our paper just entitled Enriching Version Increments with Engineering Intent for Enhanced BIM Model Checking Workflows. So let's directly jump into the topic. We have looked into the workflow of BIM-based model checking, where we traditionally have a model author who creates a BIM model with established tools. And once the design has evolved to a specific state, the model is sent over for coordination and review to a BIM coordinator or respective role. The BIM coordinator then uses established software products like Solibri and sets up a couple of rule checks that should be performed. The model is then assessed against these rules, and afterwards the BIM coordinator has to manually review the outcomes or the results of these rules and has to decide whether or not we need to create some BCF issues or some topics that need to be incorporated into the design. So ultimately, we typically have a set of BCF issues that are then sent back to the author, and the author is then responsible for incorporating the requested changes into the BIM model. So eventually we have a new version of the BIM model. This new version is then again sent over for coordination and review. And what we can already see here is that we perform essentially the same checks. However, what we can already see in this mockup is that here, for example, rule 1 failed in the first run, but passed the second version, whereas rule 5 was evaluated positively in the first run and now returns an error or some warning that needs to be evaluated. So far with existing technology, we don't really have any opportunity to perform reasoning on this situation. So what we can summarize here is that we say we do not have any tracking opportunities of perform changes or any opportunities that sets changes into the relation to the previously detected issues. And that's essentially the research gap that we have investigated in this paper. We acknowledge that there is already very established tooling and workflows available for BIM-based model checking. However, with each new model version or iteration that we have, we actually see a full re-execution of the entire rule set, and that is executed for each new model version. So what we are presenting in this paper is actually a link between an incremental update description together with the model checking process itself, and in combination we can then also perform reasoning about the model checking results and then also link the results back to the actual updates that have been performed. Our overall proposed method still considers the designer as a standalone entity in the workflow and the model checking or the coordination on the right side. So the designer still has the full responsibility for the design or the BIM models itself. However, we are not sending entire BIM models every time we are actually going into the model checking part, but we are using a graph-based version control mechanism that essentially abstracts the changes, so only the modified parts, into an increment that we are labeling here as PIJ, so describing the changes from version 1 to the other version. Before moving then into the model checking system itself, we are introducing a so-called increment interpreter, which takes the raw information that is given in the increment and enriches this increment with additional engineering logic, which we'll discuss more in detail on the next slide. And with this enriched representation of the version increment itself, we are then going into the model checking, and we have an assignment module which selects exactly those rules that need to be re-executed based on the content that we see inside or based on the output that the increment interpreter has given us. Last but not least, we are also linking the rules with the issue reporting itself. For this, we are introducing a reasoning module. In the next steps, I'd like to further introduce these three new modules, so the increment interpreter, the assignment module, and the reasoning module. Let's start with the increment interpreter. As I already said, the version increment itself is pretty much raw data, so it describes which entities or which information has been either removed or newly inserted in the BIM model, but this really happens on the level of entity instances, so it's pretty much no engineering intent at all that we can directly derive from that, and that's the target of this increment interpreter. For this, we have set up a so-called operation library, where we always have a graph pattern and a classification, so something that this graph pattern is describing. And then the increment interpreter essentially does nothing else than looking for these patterns that we have in the operation library to derive, on the one hand, the so-called targets, so the element identifiers or the identifiers of those elements that actually have been modified or altered, and also the so-called modification scope. So we can derive information about whether there was a geometry removal or there was a change in material, a change in placement, new properties being inserted, and so on and so forth. And that's kind of a classifier that we get out of this step. We can really say, okay, this is the engineering quality of changes that have been applied here to this BIM model. Having the target and modification scope at hand, we can then move into the assignment module. So the assignment module is responsible for selecting the rules that need to be re-executed based on the changes that have been performed to the model. So we take the target, so the elements that have been changed, and map them to the so-called application target and the model context of the rule. The application target itself can be understood as like a primary filter. So we can say, well, we have a rule for all the windows, for all the walls, or something like that. However, for some rules, we also need a secondary source of information, so a couple of other model information, other elements that kind of support this rule. So we can say, if we have a clash detection, typically we have one leading element type and one supporting element type. So this goes into the model context. And in addition to the actual checking process, which is of course also in the rule setup, we also have a scope, which is again like this classifier that says, okay, under which condition or under which criteria does this rule need to be re-executed. If the rule exclusively tackles geometric aspects, well, we don't have to re-execute this rule if we are sure that nothing has changed in the geometry. Whereas if the rule follows a geometric aspect, and there was only changes in properties or material information, then we can actually selectively trigger these rules based on what the increment interpreter has reported to us. This brings two advantages. The one hand is that we actually map the specific model elements which underwent changes to the respective rules, and we also have a scope execution, so we only execute the relevant checks all over again. If we have done this, we can move on to the reasoning module, which then links the results that come out of the rules to the respective topics. For this, we can actually look into three main categories. On the one hand, we can say if there are new elements being inserted into the model, we select, of course, those rules that need to be applied to these new elements. If they pass the rules, everything is fine. If they fail, this is a clear indicator that we actually need to open a new topic or a new issue. If we have elements that have been removed from a model, we can either say, okay, if there were failing issues in the past, it's likely that we can remove or close these issues. If the elements were like in the primary scope, if they have served as the model context, there's also a chance that we need to close other issues. So we have to look in both the pass and the fail part, and it's a bit more complex with modifications to elements that have been already in the model. There again, we can check if we have already seen or created issues in the past. If these issues are now resolved, so the rule delivers a pass result, we can label this open issue from the past runs as in progress. If they are still failing, we can either say, okay, has it passed before? Then we need to open a topic. If it has failed in the past and still fails, we can still label this issue as in progress, that we indicate the system operator to say, okay, well, at least there was some progress to this specific issue. So to sum it up, what we have presented here is a first framework towards change reasoning interlinked with the actual model checking. While we were able to establish links between the issue description itself and the performed modifications over this intermediate step of the rule descriptions. And overall, we are featuring a human-in-the-loop principle in this scenario. So we are not aiming to automatically close or process issues, but it's really meant to do a pre-selection of issues that are likely to be affected by the model changes that have been introduced. Of course, there's always future work. So what we need to do is that we focus more on complex rules. So far, we have mainly worked with rather simple, explicit rules. But especially if it's going into the direction of fire safety or evacuation scenarios, there is a lot more complexity in the rules that we have not tackled so far. And overall, we can also say that, well, this is just a starting point for a bigger project where we really want to use all the information that we're gathering in this framework to also learn from decisions, from resolutions, to also propose solutions to upcoming new problems in the future using learning approaches. And with that, I thank you for your attention and I'm open for your questions.